the last class, we talked about existential quantifiers and universal quantifiers. We defined them and we talked about them in brief, existential and universal quantifiers. And from this session, we'll start with some examples where you will be able to determine the truth value of a certain propositional function given the specific quantifier used on it. Okay, let's look at this example. So the propositional function that we have here states that y cubed is less than 18 for all positive integers not exceeding 3. For all positive integers not exceeding 3. In this case, let's say our domain for quantifiers. Remember, we always have to specify the domain. For this specific example, so our domain can be all positive integers not exceeding 3. So for this specific propositional function, if we apply a quantifier on it, we have to specify the domain, right? Let's say the domain is all positive integers not exceeding 3, as it says in the propositional function itself. Okay? So if that is our domain, can you guys tell me what are the elements of this domain? Can anybody tell me?
1 and 2.
1 and 2. Not exceeding 3. Pay attention to the details. Not exceeding 3. So is it going to be just 1 and 2?
1, 2, 3.
Yes.
Not exceeding 3. Not exceeding 3. That is, it cannot be greater than 3. But 3 can be there. Right? So it's going to be 1, 2, and 3. Not exceeding. Pay attention to the details. Okay? So it doesn't say that all positive integers less than 3, all right, or up to 3. Even for up to 3, you'd have 3. It says not exceeding, which means all positive integers that are not greater than 3. 3 is not greater than 3. Okay? So technically, 1, 2, 3, these 3 numbers should be in the domain, all these 3 numbers.
Miss,
Yeah.
excuse me. Miss, here it's written not exceeding 3. It's not written not exceeding or equals to 3.
Yes, exactly. That's why you can have 3 in the domain, right?
It's not written equal to 3, miss. Like not exceeding. That means like 2.99 or say 2.9 will be the limit, right?
No, this is an integer.
Oh, okay.
Not exceeding 3. That is, you cannot go past 3. However,
Oh, okay, miss.
However, 3, the number 3 itself does not exceed itself. It's equal, the 3 number itself, it does not exceed itself, right? So in the domain, you can have 3. So not exceeding 3 means including 3. Okay, okay, so all positive integers not exceeding 3. In the in the exam, for such cases, if you're confused, make sure to ask questions and to clarify if you're not sure about what it means, okay? Instead of just going ahead and specifying the domain based on your understanding, if you're a bit confused, then make sure that you ask questions and clarify what it means, okay? If you're not clear with the meaning. So the domain consists basically of 1, 2, and 3. If that is our domain, and we have to find out the universal quantification of this propositional function, the truth value of the universal quantification of this function for this specific domain, how do we do that? The universal quantification of this function is equivalent to what? P1 and P2 and P3. Why? Because 1, 2, 3, these are the elements. These are all the elements of the domain. Okay? And in order for the universal quantification to be true, what is the condition here? For the truth values of P1, P2, P3.
They all have to be
All
true.
should be true.
They all have to be true. Very good. In order for the universal quantification to be true, the truth value of P1 and P2 and P3, all of them has to be true. That's why we have the AND operator here. That is why we have the AND operation. So now let's see if the truth value of P1 and P2 and P3, if indeed the truth value is true or false. Okay, for P1, first of all, what do we have for P1? For
1
P1,
cube.
1.
you have y cube is 1 cube, which is 1, which is less than 18. So is P1 going to be true or not?
It's true.
It's true because it's less than 18. So P1 is true. What about P2?
8. 2 cube 8. True, also true.
Also true. And P3,
3 cube is
False.
27. That's false, ma'am.
because 3 cube is 27 and 27 is not less than 18. So you see, P1 is true, P2 is true, however, P3 is false. All right. Now, since P1 and P2 are true, since these two are true, the universal quantification is going to be true, right?
No, miss, it's gonna be false.
Very good. It's going to be false. Why is that?
Because
Because-
P2 is false.
Because for universal quantification, all the proposition has to be true for all values from the domain, all values from the domain. However, we see that even though these two are true, P3 is false. One of the values of the domain give us false for the proposition. So that's why the universal quantification is going to be false, in fact. So you see, that's why it's very important to understand the domain. The domain is as important as the proposition itself. It's as important as understanding the propositional function. If you just misunderstood the domain and had only 1 and 2 in the domain, then you would get completely different truth value here. It's very important to understand the domain and specify the domain. Excuse me. Now, here P3 was the counter example. That one example which disproves the universal quantification. So P3 was your counter example. Okay, can you guys tell me what if for the same domain and for the same propositional function, we use the existential quantification this time?
Means
What
then
happens?
it will be true.
Existential quantifier will be true
Why is that?
because only
Because
one
it
of the propositions need to meet the truth value.
Yes, only one of the propositional function has to be true at least one of the values from the domain. The propositional function has to be true for at least one value from the domain. As we can see, it is true for one of the values of the domain. It's true, in fact, for 2 of the values of the domain. So at least one condition is fulfilled. Existential quantification is true, even though this one is false. Okay, so that's what we have here. The same propositional function, and for the same domain, the existential quantification is equivalent to the OR operation of the propositions at every single value of the domain, P1 or P2 or P3, because as long as at least one is true, the whole thing is true. When will this be false, guys?
If all of them were false.
Yes, the existential quantification would be false only when the function is false for all values of the domain. Okay. However, here it's true for 2 of them, so it's true. Now, what if the domain was all positive integers greater than 2?
Then it would be false.
First of all, what would you have in the domain now?
3 and more.
Real numbers starting from 3.
Real numbers?
All positive integers
Integers
from 3.
starting from 3. That is 3, 4, 5, 6, so on until infinity, right? Yes, and the lowest value in this set, the lowest value is what?
3.
3. And even for the lowest value, as you can see already, the proposition is false. So it's definitely going to be false for higher values, because what is the statement? The statement involves y cube less than 18. So if it's false for the lowest value, which is 3, it will definitely be false for the higher values. So you cannot find even one value from the entire domain when the domain is all positive integers greater than 2. When the domain is all positive integers greater than 2, you will not be able to find even one value from the domain for which this propositional function is going to be true. So the existential quantification for this function, for this specific domain, the second domain, all positive integers greater than 2, for this domain, this quantification is going to give you false. All right. So, and if existential is false, universal will obviously be false. So yeah, you see, again, domain is as important as the function itself. What about this one here? What about, let's go with the domain of real numbers here. for all x present in the set of real numbers. R represents what? R represents the set of real numbers. X present in the set of real numbers. So the domain is all real numbers. For the set of all real numbers, we have to find out whether the universal quantification of the expression x equals to x plus 1 is true or false. Okay. When the domain is the set of all real numbers. What do you guys think? Is this going to be true or false?
False, I guess.
False.
False. Very good. It's going to be false. X equals to x plus 1 is a condition that can never be met. It's an expression that will never be true. Okay. For real numbers, because you will never find a real number which is equal to an increment on it, right? It does not make sense. So, yeah. This is going to be false. The universal quantification of this expression is going to be false for the given domain. What about existential quantification? Will even existential quantification be true? Guys?
No, ma'am, it's false.
Yeah, you cannot find even one example. So even existential quantification would be false. Okay. When can we say that two statements involving predicates and quantifiers are equivalent, are logically equivalent? Look here, for example, these two statements, you have one on the left-hand side, another one on the right-hand side. These two are logically equivalent. And when can we say that they are logically equivalent? When, regardless of whichever predicate or whichever propositional function you use here, and whichever domain is used here for both these statements, they still have the same truth value. That is, whichever propositional function, whichever propositional function you use for px, whichever predicate you use for px, and whichever predicate you use for qx, and whichever domain you use for these two statements, if they have the same truth value, regardless of that, then we say that they're logically equivalent. Bear in mind that the specific propositional function or the specific predicate that you use for px here in this statement, it's going to be the same predicate here in the second statement. Same goes for qx. Whichever you use for qx, you are allowed to use whichever predicate you want for qx. But the one that you use on the left-hand side will be the same on the right-hand side. Same goes for the domain. You're allowed to choose whichever domain you want, but both of them will have the same domain. Okay? So whichever domain you use or whichever predicate you use, as long as the statements have the same truth value, they are logically equivalent. Now, for this specific example, I'll show you how to prove that these two are equivalent by logical reasoning. Before that, remember that two statements are equivalent when we can prove that the biconditional between those two statements is a tautology. Remember? When will that biconditional be a tautology? When you can show that the conditional in both directions is a tautology, basically, right? So first you have to show that if the left-hand side is true, then the right-hand side is true. That's the first thing that you have to show, right? But are we done there, guys? Is that going to be enough?
No, but then we have to show that if the right-hand side is true, then the left-hand side is also true.
Very good. We have to go in the other direction as well, right? So basically, that is what we are going to do here. In order to prove that these two statements are equivalent to each other, first we will show that the left-hand side, if the left-hand side is true, then the right-hand side is also true. Then we will also prove that if the right-hand side is true, then the left-hand side is true. So once you prove that the conditional statement in both directions are tautologies, it means that the biconditional between these two statements is a tautology, which means that these two statements are equivalent, are logically equivalent. Okay, so let's start with the first one. So for the first one, we will start with the hypothesis or the assumption that the left-hand side is true. Now, if the left-hand side is true, from here we have to get to the point, or we have to get to the conclusion that the right-hand side is also true. So what is the expression on the left-hand side? The expression on the left-hand side is, as you can see from here, for all x, px, and qx. So we'll start by assuming that the left-hand side is true. And from there, we have to get to the conclusion that the right-hand side is also true. So the statement is for all x, px, and qx is true. That is, for all possible values of x from the domain. Now, whichever domain you pick, again, for all possible values of x from the domain, px and qx is true. That is our assumption. For all values from the domain, for all values of the domain, this is true. Now, if this statement, px and qx, this statement is true for all values of the domain, whatever statement this is, it doesn't matter. But if this is our hypothesis that it's true for all values of the domain, then now if you pick any variable, any element a from the domain, any variable a from the domain, if you pick that from the domain, as long as it's from the domain, we can say that the statement is true for this variable because it's from the domain. What was our assumption? That the statement is true for all x's from the domain. For all values of the domain, this statement is true. Now, a is in the domain. Any variable a, as long as it's in the domain, the statement is true for a, right? So we can say that for any a in the domain, PA and QA is true. Since a is from the domain, and since our assumption, based on the assumption, we are saying that this statement is true for all values of the domain, and a is from the domain, we can say that PA and QA is true. Everybody with me so far? Any confusion?
Ma'am, I actually have a question.
Yes.
In the previous example, we actually used the domain, and we've got that the values of x will be 1, 2, and 3.
Yeah.
So for the third element, 3, it was a false.
Yeah.
So what there is an element like that in this domain?
But see, that is the point here. In order for these two statements to be true, we're saying that they have to have the same truth value regardless of the domain. See, this entire statement, the one on the left-hand side, can be true or false.
Yes.
But whichever truth value it has, the one on the right-hand side has to have the same truth value. That is the point here. Okay?
Okay, ma'am. Yes,
So
ma'am.
based on the domain, it can be true or it can be false. But whatever truth value it has, the right-hand side has to have the same truth value in order for them to be logically equivalent. This is about logical equivalency here. That's why. Now, in order to prove that they're logically equivalent, we have to prove the conditional statement from the left to the right. That is, if the left-hand side is true, then the right-hand side is true. Here, even though the domain hasn't been specified, we can say this because our assumption, we are allowed to make a hypothesis. Remember, in a conditional, we start from a hypothesis, we get to a conclusion. This is our assumption, this is our hypothesis, an assumption. And based on this assumption, all values, for all values from the domain, this statement is true. Now, since it's true for all values of the domain, we can pick any variable a from the domain and say that the statement is true for that value. Since it's true for all values, it must be true for a as long as it's in the domain, right?
Yes, ma'am. Got
So
it.
any variable a in the domain will give us PA and QA is true. Now, PA and QA, if this is true, what can you say about the truth value of PA? Can PA be false?
No, miss, it has to be true.
Why?
Because there is
Because
and
it's
op-
an operator.
Exactly. Because it's an AND operation, PA has to be true. Same goes for QA. QA has to be true. Because this statement is true and there's an AND operation here, PA, QA, each of these individually have to be true. Now, PA is true. That is, if you pick any variable A, any A from the domain, as long as it's in the domain, PA will be true. Any A, for any A, PA is going to be true. When will this be the case? When can you say that I can pick any A from this domain and PA will be true? Only when it's going to be true for all values in the domain. Yes, that's only when you can say something like this. Saying something like this, that for any variable A, you can pick any variable in the domain, from the domain, and it's going to be true. You can claim something like this only when it's true for all values in the domain. So if it's true for all values in the domain, we can say that for all x, px is going to be true. Same goes for qa. If you can say that qa is going to be true for any a that you pick from the domain, you can say that. You can claim something like this only when it's true for all values in the domain. Only then you can say something like that, right? I can just close my eyes, pick any variable from the domain, as long as it's from the domain, it's going to be true. Only when it's going to be true for all values from the domain. So for all x, qx is also true. So these two are true individually. Since these two are true individually, we can say that the AND operation between these two is also going to be true. Since PA is true and QA is true for every element in the domain, we can say that for all x, px and for all x, qx is true. Since these two are individually true, the AND operation between these two will also be true. So see, based on the assumption that this is true, we got to the conclusion that this is also true. Okay. Just a conditional. Again, don't get confused here. It doesn't necessarily mean that this statement is a tautology. That is, this statement will always be true. Whether this statement is true or not depends on the domain and the predicates. Here, we are assuming, this is an assumption, assuming that this is true. And based on the assumption, we have concluded that this is also true. So this is a conditional expression, okay? All right. Now we have to do the same thing in the other direction. We have to start with the assumption that the right-hand side is true. We can start with the hypothesis that the right-hand side, the statement on the right-hand side is true. And then from there, we have to be able to get to the conclusion that if this is true, then the left-hand side is also true. Okay. So if the statement on the right-hand side is true, what is the statement on the right-hand side? For all x, px and for all x, qx is true. Now, if this is true, what can you say about the truth value of for all x, px, guys? Can it be false? For all x, px, for all x, px, just this part, just the first part, can it be false for all x, px?
No, ma'am.
No, ma'am.
Same reason, because there's an AND operation here. So these two have to be true individually. So for all x, px is true and for all x, qx is true. Now, if for all x, px is true, for all x, px is true, if that is the case, that is, for all values in the domain, px is true, in that case, we can pick again any variable a from the domain and it's going to be true. Because a is in the domain, we are saying that this is true for all possible values of x. That is, for all values in the domain. So as long as a is from the domain, for any variable a, pa is going to be true. Same can be said for this one. qa is going to be true for any variable a. And now since these two are true individually, since these two are true, since the statement, the propositional function is true at a and the propositional function q is true at a, we can say that the AND operation between these two statements at a is also going to be true. That is, pa and qa is going to be true as well. And since you're saying that this statement, pa and qa, is going to be true for any variable a in the domain, you can say that only and only when it's true for all values in the domain. And in that case, we can say that for all x, px, and qx is true. So this is how you lay down your logic. Okay. So when you first look at it, when you first look at the statement, what it's saying, that for all x, px, and qx is equivalent to for all x, px, and for all x, px, and for all x, qx. The statement, in the first glance, you would say that this is very obvious. Okay. Obviously, it's going to be true. For all x, px, and qx, if this is true, then for all x, px, and for all x, qx should be true. It makes sense. However, here, we don't go by this statement. It makes sense, or we don't go straight ahead, go ahead and say that it's obviously true or something like that. We lay down our logic. Okay, we lay down our logic as to why we said that. And this is how you would have to do it using propositional logic. Okay, using propositional logic, this is how you would have to do it. Okay, so since we have proved the conditionals in both directions, we can say that these two statements are equivalent. Again, remember, we are not claiming that any of these two statements are tautologies or contradictions. That is, we are not claiming that this will always be true or this will always be true. We're saying that whatever truth value the left-hand side has the same truth value, the right-hand side will also have. Okay. Now, moving on to negation of statements involving predicates and quantifiers. If you have a statement, something like this, you have quantifiers and predicates. Now, if you have a negation applied on this entire expression, how do you do that? First, we apply the negation on the quantifier. We basically move from left to right. And on the far left, you always have the quantifiers, right? So we have to move from left to right. And the first thing we find is the quantifier. So first you apply the negation on the quantifier. And how do we do that? When you apply the negation on a quantifier, you just convert it to the opposite. If you have a universal quantifier, you convert to the existential. If you have an existential, you convert to the universal quantifier. Okay? So you apply the negation on the quantifier first. Here we have universal quantifier. Negation on universal gives us existential. And then the negation is applied on the next part of the expression. What is the next part of the expression? What comes second? What comes next? The predicate itself. So you apply the negation on the predicate itself. Okay. So same goes for the existential quantifier, converted to universal once negation is applied, and then the negation is applied on the predicate. Now, let's look at an example. Let's say the predicate or the propositional function represents the statement x equals to 0. This is the predicate, okay? So if you have to apply the negation, first the universal quantifier will be converted to existential quantifier, obviously, and then the negation will be applied on the predicate. And how do we apply the negation on the predicate? The function that you have inside, whatever statement it is, you have to write down the opposite statement. X equals to 0 is our statement here. What is the opposite statement to x equals to 0? X not equal to 0. So there you go, negation. Any questions regarding negation?
No, ma'am.
Okay. So yeah, we'll circle back to this puzzle at the end of the lecture. If I forget, please do remind me to circle back to this puzzle. Nested quantifiers. So far, you've worked with either with just a single quantifier, or even if you had multiple quantifiers, all quantifiers were of the same type. You actually didn't have to even evaluate an expression where there are multiple quantifiers where the domain has been specified, okay? So far, the examples of quantifications that you have evaluated, the truth values of which you have evaluated, had only one quantifier, right? The only example where you had multiple quantifiers, that one, you haven't actually evaluated the truth value of this one at all. This is just a proof, okay? So when you have a statement where there are multiple quantifiers, and you have to apply the quantifiers following a certain order, even here, even though there are multiple quantifiers, this is not an example of a nested quantifier. Because see here, here where in this statement where we have multiple quantifiers, it's still clear that you apply the universal quantifier on this predicate and the universal quantifier on this predicate separately, and then compute the result. What if you have to apply more than one quantifiers at the same time? That is, what if we have an expression like this, something like this? Then we call this a nested quantifier. In nested quantifier, the order of the quantifiers is very important. And by that, I mean the position of the quantifier. Here you see the existential quantifier comes first. The universal comes second, all right? So the truth value, so far you have seen that the truth value depends on the propositional statement, or sorry, the propositional function, the domain that has been specified, and then the universal quantification, right? Here in nested quantification, the truth value depends on all those things, yes, but also on the order of quantifiers, all right? Here you have the existential quantifier coming first and the universal quantifier coming second. This has a specific meaning. Because you have something like this, there's a way we have to read a statement like this. So here you have at least one y, all x plus y equals to 0. But what does this mean? It means that there exists at least one y such that for that specific y, for that specific, the keyword here is for that specific y, all values of x's, for all x's, for all values of x, you will get x plus y is equal to 0. Let's say here our domain is the set of real numbers. Then this statement says that for the domain of real numbers, this statement says that there exists at least one real number y. There exists at least one real number y such that for that specific real number, the summation of that, such that the summation of that specific real number and all real numbers x, all real numbers represented by x, you will get 0. The summation of that specific real number and all real numbers x, you will get 0. Okay? So this is very important. This is very important to understand what it means based on the order of the quantifiers. Here, you have to find at least one real number for which real number, that for that specific real number, you get x plus y equals to 0 for all x's. This statement is in fact false. Why is that? Because if you think about real numbers, there is no such real number which will give you x plus y is equal to 0 for all real numbers x. That is, you have to find whichever real number you pick for y, whichever real number you pick for y, for that specific real number, all other real numbers added to it will give you 0. Is there any real number like that? Let's pick an example. Let's go with 1, for example. If you pick y is equal to 1, what do you have to show? You have to show that all real numbers, when summed with y, gives 0. All real numbers. 0 is in the set of real number. Is 0 plus 1 equals to 0?
-1.
Yes, -1 is there. -1 is the only real number. -1 is the only value of x for which y is equal to 1 will give you x plus 1, y is equal to 0. However, here it says for all. For all. Your example, x equals to -1 is not going to be enough. Why? Because we have for all here, for all. At least one y such that for that specific y, all x's will give you x plus y is equal to 0. So this has to be true for all x. Okay, for all x. So you cannot find even one real number for which all the real numbers added to it gives you 0. Yes, if you pick y is equal to 1, x equals to -1 gives you x plus y is equal to 0. But what about the other x's? We have to prove it for all x, right? No, we cannot do that for all x. What if you pick another different example of y? Give me any other example of y. Go with 4, 5, 4.5, -4.5, whatever you want. Any real number you pick for y, for that specific real number, you have to show that all x's give you x plus y is equal to 0. You guys tell me, is there any real number like that? Is there any magical real number like that?
No, man.
No, there isn't. So this statement is false. That's why. Any question or confusion regarding this? It's very understandable if you have any confusion here. Nested quantifiers are a bit tricky. So if there are any questions, go ahead. Shoot. Okay. So if this is clear to all of you, in that case, what happens when we switch the position of the quantifiers? I'm not talking about the variables. If you keep the position of the quantifiers the same, that is, if you still keep the existential first and the universal second, and you change the position of the variables, either here or here, it will have no effect whatsoever because they are, at the end of the day, variables coming from the same domain. Nothing changes. However, what happens when we change the position of the quantifiers, switch the position of the quantifiers? What if I put the universal one first and the existential one second? Will it have the same truth value then? Before going to truth value, will it have the same meaning?
No, ma'am.
No, ma'am.
Does everybody agree?
Yes, ma'am.
Then we will interpret it as for all values of x there is at least one y for which x plus y equals to 0.
Yes.
So it will be the same, right?
It will be the same? Okay, let's see, Fahad, if it's going to be the same or not. So you're saying if we reverse the position of the quantifier, it's going to be for all x, for all real numbers x, there exists at least one real number y such that x plus y is equal to 0. That is for all real numbers. Every single, what does it mean? It means that for all real numbers, that is every real number must have at least one real number which when added with it gives us 0.
Means
For
the
all
answer will be
real,
false.
True.
This is gonna be true, right?
How is
Because it says at least one real value of y. So
If we
at
take like x equal to
is the
2, then our
keyword.
y will be equal to -2. If 3,
As
then
the-
-3. 4, then -4.
yes, you guys have a very, you guys are kind of heading in the right direction, but let's see. Let's just still explain to make this clear for everybody, okay? So yeah, you are correct when you say that it's going to be true. Because the moment we switch the position of the quantifiers, now the meaning is for all real numbers x, for all real numbers, there exists at least one real number. For all real numbers, there exists at least one real number such that x plus y is equal to 0. And it is true. Every real number has an opposite, right? Every real number has a negative. Every real number does, right? 1 has a -1, 2 has a -2, -3 has a 3, -4 has a 4. And then 0 has 0. And 0 plus 0 is equal to 0. Even for fractions, every real number has a negative, right, guys?
Yes, ma'am.
So the statement says for all real numbers, there exists, for all real numbers, there exists at least one real number such that x plus y equals to 0. And it is true, because for every real number x, every real number of x, you will be able to find one real number y. For every real number x, you will be able to find one real number y such that y is equal to -x. For every real number, you'll be able to find that. Every single real number has exactly one negative. And we need only one because existential, at least one. So we have at least one real number for all real numbers. So for all real numbers x, there exists at least one real number which will give you x plus y equals to 0. And this is true because every real number has one negative or one opposite, one real number that's the negative of it. All right. That's why this statement is going to be true. Okay. So does it make sense now, Fahad? If it doesn't make sense, please go ahead and tell me that. All right. Yeah.
I got it.
Yeah. Okay. Very good. Okay. Does it make sense to everybody else? If you have any questions, go ahead and ask. It's very understandable if this is tricky because nested quantifiers are tricky for most students. Okay. So nobody has any question. In that case, we can move forward. How to apply negation on statements involving nested quantifier. So let's say we have a statement like this. Nested quantifiers, right? You have nested quantifiers here. Multiple quantifiers combined together, you have to apply them on the statement. So nested quantifier, how do we apply the negation? It's the exact same process. You move from left to right. You go with the first part of the expression that you find when you move from left to right. The first thing we find here is the universal quantifier. The negation of the universal quantifier will be what, guys?
An existential quantifier.
Exactly. It will convert to the existential quantifier. And then the negation operator moves to the next part. What is that? The next part, the second part is the existential quantifier. Now we have to apply the negation on the second part, which is the existential quantifier. And once we do that, it converts into the universal quantifier. And then the negation moves into the predicate. That's what we have left, and it moves to the predicate. The predicate is xy is equal to 1. The opposite of this will be xy not equals to 1. So the negation applied on it gives us this expression finally. Okay. Make sense? Anybody has any question regarding negation or how to apply it? Excuse me.
Miss, so basically, if we apply negation, we just reverse the quantifiers, right?
Yeah, we move from left to right. We take one at a time. And for the quantifiers, we just reverse the quantifiers. Yes, correct.
If there was a greater than, then is less than.
Inside the predicate, yes, whatever statement you have inside the predicate, you'd have to reverse it. If this was xy greater than 1, the opposite would be xy less than or equal to 1. Not exactly less than, all right? The opposite of greater than 1 is less than or equal to. So yeah. Make sense so far? Anybody has any questions? Okay. In that case, can you tell me what this statement means and whether this is going to be true or false? This statement, for all x, at least 1 by xy equals to 1. Let's go with the same domain from the previous example. Real numbers, the domain of real numbers.
Ma'am, it's true.
It's true.
Yes.
Does everybody agree with him? Is it true? Really?
Yes, ma'am.
Yes, Miss, it's true.
Nobody thinks it's going to be false.
No, Miss.
No.
Okay, so let's see, first of all, what it means. So it means that for all real numbers x, there exists at least one real number y such that xy equals to 1. That is, every real number has at least one inverse. Basically, it means that, right? Every real number has at least one real number which will give, the product of which will give 1. xy is equal to 1. And this is true, just like you guys said, because every real number does have an inverse. If you have 2, there is 1 by 2. If you have 3, there is 1 by 3. If you have minus 3.5, there is minus 1.35, right? So every real number has an inverse. So that's why this statement is true. Does it make sense to everybody that this statement is true?
Miss, I have a question.
Yes, go ahead.
Just for example, if x is 3, then y has to be 1 by 3, right?
Yeah.
So is 1 by 3 a real number?
Yes, it is. Why would it not be a real number? You can place it on the number line, yes?
I thought it was integer, that's why I
It's not an integer.
We're not talking about the domain of integers. We're talking about the domain of real numbers.
Okay, Miss.
So 1/3 is a real number, all right? All rational, irrational, integers, non-integers, all of them are real numbers, all right?
Yes, Miss.
Okay. So yeah, does it make sense?
Oh,
Yeah.
Miss, what happens if it's 0? Like if it's 1 by 0?
1 by 0. Is
Yeah.
1 by 0 a real number though?
No, but if x is
If x is 0, then
yeah,
what about
x,
the
if
whole
x is 0, then
thing?
what happens?
Yes, very good. If x is 0, what happens then? If x is 0, y, what can you bring for y which will give you xy is equal to 1?
Miss, 1 by 0?
1 by 0. But again, 1 by 0, is that a real number?
No, Miss.
No, it's not a real number. So, for this specific example, if we have the domain of real numbers, 0 is a real number. And for 0, just like one of you mentioned, I think it was Nafisa, right? Yeah, just like Nafisa mentioned, what happens when x is 0? For 0, is there any other real number which will give you xy is equal to 1? Is it possible to find a real number
No, ma'am.
which will give you xy is equal to 1 when your x is equal to 0?
No.
No, it cannot. So you see, even though initially it was clear as day to all of us that this was true, but you see, there's a counter example. You have to always, when you have these things in the domain, think about the tricky examples. Think about, see, we went with the positive values, we went with the negative values, we went with the fractions, but 0 is there as well. Always think about these values. Okay, take one positive, take one negative, based on the domain. If the domain allows negative values, that is, if the domain allows positive values, take one positive, take one negative, take one fraction of both positive and negative, and always take 0 if it's there. Okay? And for 0, as you can see, just for 0, for the domain of real numbers, this statement is false. Okay? Now, does it make sense to everybody?
Yes, ma'am.
Okay. All right. What happens when the domain is changed to the set of all integers, all positive integers? Then we don't have 0 there, right? In case of the set of all positive integers, 0 is not there for positive integers. Then the statement becomes true, right?
No, ma'am.
No, Mrs. B, it becomes false. Because it
Why is that?
false.
Because it's an integer. Exactly. Very good. In case of integer, for the set of integers, are fractions going to be allowed? No, the fractions are not going to be allowed. So for all x, at least one y that we had, for that y, if fractions are not allowed, then for all x, you cannot find at least one y where xy is equal to 1. You cannot have that because fractions are not allowed. So that's why you cannot have the inverses here, and that's why xy equals to 1. This statement is not true when the domain is the set of all integers, all positive integers. What about the set of all integers? Even there, it's going to be the same because it's integer. Fractions are not allowed. Now, what about if the domain is all positive real numbers?
Yes, Miss, it will be true in this.
For positive real numbers, what will be the situation there?
It will be true. The statement will be true.
Yes, because other than 0, there are no issues. Same goes for the negative real numbers. For negative real numbers, what will we have? Same situation. For negative real numbers, since x, y, both of them are negative, there's no problem with the sign, and since both of them are allowed to be negative. So for all x, there does exist at least one y, which will give you xy equals to 1 for the domain of negative real numbers. So yeah, very good, Nafisa. Okay, now you guys tell me what happens for this same predicate if we reverse or switch the position of the quantifiers. That is at least 1x, all y, xy equals to 1. What if we reverse the position of the quantifiers? What happens then? For the same domain. Let's say, let's go with all negative real numbers.
Miss, it's false.
Does everybody agree with him that it's false? Nobody thinks that it's going to be true.
Ma'am, can you repeat the domain?
The domain is going to be the set of all negative real numbers.
Ma'am, it's going to be true.
It's going to be true. We are switching the position of the quantifier. Now it's saying that at least 1x, all y, xy equals to 1. That is, there exists at least one, excuse me, there exists at least one negative real number, x, such that for that x, all negative real numbers multiplied with it will give you 1. All negative real numbers multiplied with it will give you 1. Is there such a negative real number? Is there such a real number at all? Is there any such real number which, when multiplied with all other real numbers, will give you 1? All of them.
No.
No. No. You see, it's the same situation as the previous example. The moment you switch the position of the quantifiers, the moment you see, say, at least 1x all y, the moment you put the existential quantifier first, it becomes false for this specific example, for this specific expression. Why is that? Because now you have to find at least one negative real number such that all negative real numbers multiply with that specific negative real number gives you xy equals to 1. All right? So this is
xy not equal to 1.
no, I'm not talking about this expression. I'm talking about this same expression, just the position of the quantifiers reversed. All right? Okay. So what happens when the domain is the set of all positive real numbers? In that case, will it be true if we put the existential quantifier first and the universal one second for the same predicate? And the domain of all positive real numbers. Now will it be true?
No, ma'am.
Yes, it will never be true no matter what the domain is, I guess.
Yeah, you're thinking about, when you're thinking about the domain, no matter what the domain is, if you say that the domain consists of all possible things that exist in the entire, all things that exist in the entire universe. So let's not go there. The domain always has to be specified. The domain always has to be specified, but you could say that regardless of positive, negative, regardless of any real number, integer or whatever, the moment we switch the position of the quantifiers for this specific expression, it's always going to be false, because there exists no such real number such that for that specific real number, that specific real number multiplied with all other real numbers gives us 1. No, it doesn't exist. So it's going to be false. Now, what about this expression here? This expression. Is this going to be true for the set of real numbers? Think about it, guys. This one here.
Yes, it will be true.
It will be true for all real numbers.
Not for 1, ma'am.
No, miss, just except 1.
And except 1 is the important example, okay?
That's the counter
So,
example.
very good. That's the counter example. So here we are saying that there exists at least one real number. There exists at least one real number x such that for all real numbers y, xy is not equal to 1. That is, there exists at least one real number such that all real numbers multiply with it will never be equal to 1. Is never the scenario. No. What if x and y are both equal to 1?
Ma'am, আমার domain not equal to 1 করে দিতে হবে।
We're talking about the domain of real numbers. Domain change করলে তো truth value change হতেই পারে. We're talking about the domain of real numbers without changing the domain of real number, without changing the domain. For the same domain, this is going to be false, because just like Nafisa previously pointed out, there was just one example which made this statement false for the set of real numbers. 0 made this statement false. That one counter example. Similarly, for this one here, that one counter example is enough to disprove this entire statement. Okay, what is that counter example? 1. So if you have 1 here, you cannot, for x equals to 1 and y is equal to 1, xy will be equal to 1. So you do not have even at least one real number for which all real numbers multiply with it gives you not equal to 1. Okay.
But what if x is 0?
Yes, that is also another, if x is 0, in that case, yeah.
Then everything is 0, right?
Yes, if x is 0, in that case, all of this will be 0. Yeah, you're correct there. Yeah, I missed out on that one. Yeah, I missed out on that point. Yeah, very good there. So, yeah. So who was that again?
Me, Ashik.
Okay. Yeah, Ashik. Ashik, very good example there. Yeah, I'm sorry. I skipped over that. Yeah. If x is 0, there has to exist at least one real number. As long as we say that real number, 0 is a real number. This is very similar to Nafisa's example, what Nafisa pointed out. So x is a real number. In case of x, whichever real number you use here, xy, will not be equal to 1. Yeah. So very good example there. Yeah. It's exactly the same as this one here. So yeah, you're correct. I'm wrong. Thank you for proving that, and very good, Ashik, in noticing that. And the rest of you guys have to notice stuff like that as well for quantifiers. Okay, so that is why I was saying that nested quantifiers are really, really tricky. So for that, I mean, you have to make sure that you get enough, as much practice as you can. So yeah, very good, Ashik. Yes, for x is equal to 0, x is, we need only at least one, right? X is that, just that one real number for which this statement is true. For all y, whichever real number you use here for y, this will never be equal to 1. That is, the statement will always be true for x equals to 0. So yeah, you're correct. Now, what if, again, we change the domain to the set of all positive real numbers or the set of all negative real numbers? In that case, again, similar to the previous case, this statement becomes false. Okay?
Miss,
Yes.
what do we do if we find counterexamples? Do we say it's false when it was true before? If we found a counterexample?
Yeah, I mean, for example, for this one here, the counterexample was 0. Okay?
Yes, miss.
And for this one here, there is no counterexample, actually. Because just like Ashik pointed out, if x is equal to 0, in that case, for x equals to 0, the statement is true. Again, let's go back to how to read nested quantifiers. At least one real number has to exist. In order for this statement to be true, at least one real number has to exist, such that for that specific real number, all real numbers multiplied with it will never give us 1, will be not equal to 1. At least one real number has to exist. 0, there is that real number 0, which when multiplied with any real number, that is which when multiplied with all real numbers, will never give us 1, which will always be not equal to 1. Okay? So 0 is that 1, at least 1x, which makes this statement true. So there is no counterexample. Counterexample exists to disprove a quantification. Okay? So for example, for this one, 0 was the counterexample. And for this one, 0 is that specific example which makes this statement true. And it makes sense, right? It makes sense. I'm sorry I skipped over this, or I didn't notice this at first. And it makes sense because this statement is the direct opposite of this statement, right? This statement is the negated version of this, right? Think about it. This is the negation, direct opposite of this. So whatever we had here would have the opposite scenario here. Here, 0 was the only counterexample. 0 was the example that disproved this statement. Here, 0 is the example which makes this statement true. So it makes sense that it's going to be the scenario. This is going to be the case because it's the opposite, right? So yeah. So yeah, nested quantifiers, very interesting, but at the same time, it's quite tricky. Okay, any questions here for these examples? So far we've established that this statement is false for the counterexample 0. This statement is true because of the example 0. If you switch the position of the variables in this statement, it will be false regardless of whichever domain you pick in terms of real numbers, whether you pick integers, real numbers, positive, negative, whatever. And for this one here, what happens when we switch the position of the quantifiers? Can any of you tell me for this specific statement? If we switch the position of the quantifiers, that is, if we put the universal quantifiers first and the existential quantifiers second, what happens to the truth value now? This specific one is true, but what if you switch the position of the quantifiers? The universal comes first and the existential comes second. What does it mean, first of all?
For all x, there is at least one y for which the statement is
for all real numbers, all right, we are talking about the domain of real numbers still. For all real numbers x, there exists at least one real number y such that xy is not equal to 1. Is this going to be true or false, guys?
It's going to be true, I guess.
Is this going to be true? Yeah, it makes sense, right? That it's going to be true. What do you think, Nafisa?
Yeah, I'm also leaning towards true. Um, it, it should be true.
Yes, it is going to be true because this time we're saying for all real numbers x, there exists at least one real number y such that xy is not equal to 1. Okay, so the conditions are pretty lax here. Okay, for all real numbers, you can find at least one other real number. The product of the two will not give you 1. Okay, so even if you use 1, 1 for both cases, I mean, that is not exactly what the statement says. For all real numbers, there has to be at least one y. Even though for both xy 1, 1, you get 1, but there are other real numbers, right? There exists at least one other real number for which xy is not equal to 1. So yeah, this one for sure, this one I'm quite sure that it's going to be true. Because for all real numbers, there does exist at least one real number such that xy is not going to be equal to 1. Okay, you can find at least one real number for all real numbers where you can make the product not equal to 1. Okay. Yeah. Okay, so sometimes you might have to translate statements in natural language into statements involving quantifiers. Okay. So here, for example, our statement was the sum of two non-negative integers is always non-negative. So the way we translate these statements into statements or into expressions using quantifiers and predicates and other symbols in propositional logic, the way we do it is first you have to specify the domain. The domain is important. How you specify the domain, based on that, you'll draw out the rest of your expression. Now, let's say for the domain of all integers, if you say that the domain is going to be the set of all integers, in that case, think about it. What is the expression saying? It says that the sum of two non-negative integers is always non-negative. That is, as long as the variables in the summation are non-negative, the summation is going to be non-negative as well. So this is like a conditional, right? As long as the numbers are non-negative, the summation will also be non-negative. So if they're non-negative, then the summation will also be non-negative for the domain of integers. So in that case, this is how we would have to phrase it. For the domain of all integers, the expression will be a conditional statement. If x is greater than equal to 0, and if x is greater than equal to 0 and y is greater than equal to 0. If x is greater than equal to 0 and y is greater than equal to 0, then x plus y is also greater than equal to 0. This is the conditional statement that it says. For all x and all y, for all integers, as long as the integer is greater than or equal to 0, then the summation of the integers will be greater than or equal to 0. Okay. This is how we would have to phrase it based on the domain. So what did we do? We specified the domain first to integers, and then on that domain, are there any other restrictions? We have to identify that. The domain is a set of all integers. Now we have to read the statement. Are there any other restrictions on the domain? Yes, there are. They have to be non-negative. And if they're non-negative, then the summation is going to be non-negative as well. So the restriction here will be our condition, as long as x greater than equal to 0 and y greater than equal to 0. That is the condition. And if this condition is true, if this condition is met, then the expression, that is the summation of the integers, is going to be non-negative as well. So then you have this expression for all integers. This is how you would have to phrase it. Now, what if instead of using the domain of all integers, what if we used the domain of all non-negative integers? What if we said that the domain is the set of all non-negative integers? That is, for x and y, you can only pick non-negative integers, right? If the domain is all non-negative integers, then the allowed values of x and y is by default non-negative integers. In that case, what would be the expression? First of all, would we have to specify this condition? Tell me that.
No, miss.
No, ma'am.
Oh,
Because
Why
by
is that?
default it's negative.
By default, it's not more than or equal to 0. It's negative.
By default, it's negative. By default, it's non-negative. Okay, the two things mean very different things. So the by default, it's non-negative.
Yeah,
Yeah.
non-negative.
If the
yes.
domain is going to be the set of non-negative integers by default, like you guys mentioned, the values of x and y will be non-negative. So this condition does not have to be mentioned at all. All you have to do is say that for all x and all y, x plus y is greater than or equal to 0. Okay. All right. So this is how you express statements in natural language in quantifiers. Okay. Right. So any questions so far regarding all the ideas that we've discussed in this session? Okay, if there are no questions, then let's go back to our puzzle.
Ma'am,
What
can
is-
you explain me the one ax and ey? All value of x and expected value of y. এরকম যদি কিছু একটা থাকে।
Come again?
Uh,
For all x,
all x and expected value of y.
expected value, there is no such thing as expected value. At least one y, all right? That is essential. It stands for at least one y. Yeah, for all x, at least one y. Go ahead.
Then there's a statement like একটা example দিয়ে বুঝাই দেন এরকম স্টোরি দিয়ে বুঝাইতেছি
Which example? For which one?
আগে যান আগে যান
Are you
যে
talking
এখানে
about
যেমন
this one?
হ্যাঁ
Okay.
ঠিক
So,
এটাই মনে করেন
okay.
এখানে আমাকে লাইক আমি ভাঙতে পারতেছিলাম প্রথমে পারছিলাম পরে আবার একটু বুঝতে অসুবিধা হইতেছে তো বেসিক্যালি আমার অনেকগুলা ইন্টিজারের জন্য আমার একটা ইন্টিজার আসবে আর কি আপনি এক্সপ্লেইন করুন
Okay. So this was the expression, right?
Yes, ma'am.
So let's say the domain depends on the domain, right? So let's say the domain is all positive real numbers. If the domain is all positive real numbers, in that case, what does this statement mean? It means that for all real numbers x, all real numbers, there exists at least one real number y, the product of which is 1. So এই জিনিসটা বলতে কি বোঝাচ্ছে এটা হচ্ছে কি আমাদেরকে বুঝতে হবে for all real numbers x there exists at least one y such that xy is equal to 1. That is every real number for all মানে কি sorry for all মানে কি what does this for all mean? For all real numbers means that every real number, right? Every real number, every single real number has at least one real number such that the product of the two will give us 1. Okay.
Ma'am, when we say all real numbers here, we'll consider only positive ones, right?
Yeah. Very good. Thank you for pointing that out. I should have written that as well. Positive. Okay. So for every real number, if you rephrase it, every positive, you could say that every positive real number has at least one positive real number such that the product of the two is 1. Okay, so is this going to be true or not? Think about it. For every positive real number, we do have an inverse, right? Every single positive real number has an inverse. So if you go by example, the examples will never end. So what I usually recommend, if first think about, just for a basic cursory idea of the domain of real numbers, take a positive real number, for example. For the domain of the positive real numbers, take a positive integer, for example, then take a positive fraction, for example, then take 1, because that is the lowest value in the set, for example. That is the lowest integer in the set, and then maybe take a very low value of fraction. So take boundary values. Take things that go towards the boundary, basically, and then you will see that, okay, for all of this, this is true. For example, for 1, if you think about 1, for all real numbers, there exists at least 1, right? For 1, you have 1. 1 multiplied with 1 will give you 1. Okay, think about a different integer, a higher integer, maybe 5. If you take 5, for example, for 5, there is 1 by 5. There exists 1 by 5. You have, if x is equal to 5, for example, that is, if x is equal to 5, then you need what? What do you need? You need at least 1 y, which will give you xy is equal to 1. You have y is equal to 1 by 5. This is a real number. This is a positive real number. So as long as you have this, xy will be equal to 1. Okay? This will give you xy is equal to 1. Now, take a fraction, for example, any fraction. Let's say 0.325 or 325, whatever. Even that fraction will have an inverse, right? 1 by 0.325. It will give you xy equals to 1, right? So you see, first by a cursory glance, this gives you an idea. Then you go by logic. Okay, for every real number, there exists at least one real number, the product, such that the product of the two is going to be 1. Every real number, every positive real number has an inverse. Every positive real number has an inverse by the inverse law. Every real number has an inverse, in fact, except for 0. So for every positive real number, this statement is going to be true. Okay, because every real number does have at least one real number, which gives you xy equals to 1. Every real number has exactly one inverse, but that exactly 1 is going to be enough because we need at least 1. Okay, now what happens when we switch the position? Before that, let's talk about the domain of real numbers, why that was false. For the domain of real numbers, this was false because even though it's true for most real numbers, you still have one real number which acts as the counterexample, which is 0. If you take 0, for example, 0 multiplied with anything will give you only 0. It will never give you 1, right? So that's why for the example of 0, this domain, for this specific domain, this statement becomes false. Okay. All right. So far, is it making sense? If you have any confusion so far, you can ask. It's fine. I can go over it again. Fahim, so far, does it make sense?
Yes, ma'am. Yes, ma'am.
Okay. Do you see that this statement will be false for the domain of all real numbers, but this same statement will be true for the domain of positive real numbers? Do you see why and how?
Yes.
Okay. All right. Now, what happens when we switch the position of the quantifiers? What happens then? If you switch the position of the quantifiers, then this entire statement, the meaning, this thing actually is not valid anymore, because now it means a completely different thing. Now it means that there exists, because the existential quantifier came first, there exists at least one positive real number such that the product of that specific real number and all or any other positive real number is 1. Now, this is what it means. There exists at least one positive real number. At least one positive real number exists. There exists at least one positive real number such that the product of that one real number with all other real numbers will give you 1. You have to find at least one real number. You have to find at least one real number such that the product of that real number with all other real numbers gives you 1. For the domain of positive real numbers. Is there any positive real number like that? Can you find any one real number, just একটা real number, যে real number, ওই যে specific real numberটাকে যে কোনো real number এর সাথে multiply করলেই 1 পাবা, always? Is that going to be true? It's false. It's not going to be the case. That is not going to be the case. Instead of this, if you had something, if you had this, then it would be true. Because for at least one real number, there exists at least one other real number. For at least one real number, you can have at least one real number such that x y equals to 1. When x is equal to 1, y is equal to 1. All right. And also, previously what we said, the inverse law. But in this case, if you have this scenario here, for this specific case, you have to find at least one real number such that for that specific real number, ওই real numberটাকে fixed রেখে, for that real number, the product of that real number with all other real numbers, any other real number will give you x y equals to 0. এরকম কোনো real number নেই. All right. However, if we make it, let's say 0, and the domain, if we change it to the domain of real numbers, in that case, all right, in that case, Fahim, you tell me.
I can use y equal to 0.
Yes, very good.
It will give me 0.
Exactly, very good. But if the domain is positive real numbers, in that case,
it's not possible.
It's not possible, even there, right? So yeah.
Yes, it's clear now. Thank you.
All right. So anybody has any questions or confusions left?
No, miss.
Okay, all right. So I wanted to do the puzzle here at this point. However, we've run out of time. So I'll end the session here. Okay. And mind you, we're done with the syllabus for Unit 1. Okay. So you better start your preparation for the first quiz, because the syllabus